All right, here we are back again, week 5 of the course. So we are now really into the second half of the course. The end is not nigh, but it's coming in sight. And basically, we spent a lot of time getting down the technical aspects of regression analysis. Now we can use that knowledge to look into some more theoretically interesting ways of using regression analysis. So that is what we are going to start discussing today. So as always, I'll start with a bit of a recap, what we've learned and what we know now. When we talked last week a little bit more in depth about, well, how can we use multiple regression to estimate causal effects, and to what extent can we do that? And what conditions can we make stronger or weaker claims about causality? And so once we have discussed this recap, I'll do something that's a bit unusual maybe. I'll have a bit of a more theoretical reflection on what does it mean to theoretically think about causality. Specifically, I want to briefly discuss with you the concept of causal mechanisms, which is really a theoretical concept, but it's important because, well, ultimately we want to use methods to test theories. So that implies that we understand what theories say and how they work. So I'll talk a little bit about causal mechanisms and how they relate to causal effects, and how they can sometimes make more nuanced statements about potential causal effects, which specifically will lead us into two types of more advanced uses of regression analysis, namely moderation and mediation analysis. So moderation is sometimes also referred to as interaction analysis, or analyzing, estimating interaction effects, creating interaction variables. So we'll discuss that, and we'll discuss the role of centering our variables in helping us with estimating these interaction effects. And we'll talk about what is mediation analysis, and we'll see that it's a type of path analysis where we are analyzing causal pathways that lead us from our independent variable to our dependent variable. So let's start with the recap. What do we now know about how to use multiple regression analysis to estimate causal effects? Well, we know that it is a useful tool, regression analysis, to help us estimate causal effects of x's on y's, so of independent variables on dependent variables, especially in situations where we cannot assume that the values of our x variables are randomly assigned to a treatment and control group, but rather that we have to use observational data, which is usually the case, of course, in the political sciences. So we saw how we can use multiple regression analysis to prove on our estimates of causal effects over just using bivariate correlational analysis. And we also saw, well, okay, we can use it that way, but of course the question is how well does it work? And we saw that the quality of our causal estimates depends on a couple of things. And one thing that I just want to repeat, because you may forget if you're way down in the depths of statistics, that ultimately the first thing it depends on is your theoretical reasoning. So the hypothesis that you're testing, if that is based on some kind of causal story, well, did you properly deduce that hypothesis from the underlying theory? So is it really a good test of your theory? Always very important to remember. I mean, a hypothesis ultimately is also just a way of evaluating theories, but that implies that you have really thought well about, well, is it really, did I really properly deduce this hypothesis? So is it really the case that if the theory is true, that I should be seeing this causal effect in in your observations? So it's always important to remember. We also saw that we have some assumptions that we need to meet statistically in order to have a good quality estimate, and these are the 4 standard assumptions: so linearity and additivity, and independent, homoscedastic, and normally distributed errors. Yeah, so the idea that if you're estimating a linear effect where we're adding up individual coefficients, as we do in a multiple linear regression model, that it actually has to make sense to use a linear model where we're adding up the individual coefficients, that the errors in our regression equation need to be independent from each other, so there should be no systematic relationship in the value of the errors across our cases, that the errors should also be homoscedastic, so that the distribution of the errors should be constant over the values of our x variables, and that those errors also should be normally distributed, so the distribution of the errors overall should roughly follow a normal bell-shaped distribution. So that's something we discussed. Of course, also there are more fundamental issues that you always should be aware of. Yeah, of course, it depends on the quality of your data. Yeah, so sample size is, of course, an important factor in that. So, I mean, in statistics, the more observations you have, the more reliable the estimates become. So, a larger sample size is, all else equal, is always better. Of course, we have always so far assumed that our observations are a random draw from the population, so that there is no systematic difference between what we do observe in our sample and what we don't observe in the entire population. So that's the idea that we need to ensure that there is actually random selection that we can assume to have led to the cases that we observe in our sample. And of course, you want your variables to be measured validly and reliably, so that they measure what you theoretically want them to measure, and that they do so in a reliable manner. Of course, some of these things can be translated back to the standard assumptions, as to some extent we have seen. But don't worry if you don't fully understand why that is. So that's about the quality of the data itself. And one important thing, if we want to say, well, we want to estimate causal effects, then the degree to which we can actually make those causal claims based on our estimated effects depends on the degree to which we can assume that our x variables are actually exogenous. Yeah, so this is this assumption of exogeneity, and I'm consciously putting down here degree to which x's can be assumed exogenous, rather than putting down whether or not they can be assumed to be exogenous, because in practice it is often quite difficult, if not impossible, to be very confident that our x's are perfectly exogenous. So that's often a matter of degree. And it's also something that ultimately you can only say something about based on theoretical assumptions about how your x's might be or might not be related to the error term in your regression model. Yeah, remember, endogeneity, so the reverse of exogeneity, is a situation where you have some correlation between the error term in your regression model and your x variables. Yeah, so that is what we now know about how to use multiple regression to estimate causal effects and what the quality of our causal estimates depends on. So let's take a step back and let's discuss a few notes that I want to discuss with you on causal mechanisms and how they relate to causal effects. Because so far we have assumed a fairly simple theoretical world where we have independent variables, x variables, and dependent variables, y variables. And we have used regression analysis to test the effects of our x variables and on our y variables. Now, how do we come to hypothesis about these effects? Well, they are based on some theoretical reasoning, hopefully. And there are different types of theoretical reasonings that are used in the social sciences. And currently the most popular way of thinking about theory and setting up theories is what is sometimes referred to as the mechanistic approach. So this is the idea that theories specify causal mechanisms. And causal mechanisms are basically theories that connect our x variable to our y variable. So these are theoretical reasons that are behind our expectation that there is an effect of x and y. So basically it is the theoretical story that goes in between these things. Yeah, so for instance, if we say we have a theory that predicts that more income should lead to more satisfaction of the government, then that theory should specify the causal mechanisms that lead to this effect. So why is it that more income leads to more satisfaction of government? And yeah, depending on your theory, that might be some story about how more income leads people to, for instance, be overall more satisfied with their lives. And then the idea that people that are overall more satisfied with their life in general tend to be more positive about all kinds of institutions and political representation. So that's the reason why more income should lead to more satisfaction of government. And of course, there are lots of different potential causal mechanisms that could lead to this relationship between income and satisfaction of government. And so that's the idea, is that our theories specify these causal mechanisms. Again, this is one way of doing theories. There are other ways of doing theory, which I won't get into. I also won't get into why are we doing theories in this way, because there is a whole philosophical debate behind that. Why do we care so much about causal mechanisms nowadays when we talk about theories? This is something that you will definitely encounter if you go to the master's program in the more advanced methods courses. And of course, it's also something you can always ask me about in the Zoom sessions if you want to already get some kind of insights from my perspective on that. But this is basically where we are now in terms of theories. Most of these theories in social sciences nowadays are stated as causal mechanisms that follow from theoretical assumptions. So this is why nowadays we care a lot about testing for causal effects, because we tend to think about theories as being causal themselves because they specify causal mechanisms. So then it makes sense that if we want to test the theories very well, we need to look at the causal effects that are implied by those causal mechanisms. Yeah. Now we can take this reasoning can take this reasoning a step further, because often our theories will not just tell us that there is some kind of causal mechanism, but they will also tell us when this causal mechanism works and when it doesn't work, or when it works more strongly or more stronger, or when it's weaker. So in other words, often our theories will not just tell us about, yes, there is a causal mechanism that leads to an effect that we should observe from X to Y, so from our independent variable and our dependent variable, but they will also tell us under which conditions we should see this causal mechanism operating stronger or weaker, or not at all maybe. Yeah, so that's the idea, that the operation of our causal mechanism can depend on certain conditions. And these conditions can be captured by variables. So for instance, these conditions might pertain to, well, what type of people are we talking about in our analysis, if the unit of analysis are people. Yeah, so maybe our theoretical story about why there is an effect of income on satisfaction of government also tells us, well, this should be mostly the case, this positive effect of income for people with a full-time job. And not, for instance, for university students, because maybe the theory says, well, this evaluation of life satisfaction based on income, this is something that people that have full-time jobs and that aren't in an educational program anymore, that's really relevant for them. But for people that are still students, well, they don't really evaluate life satisfaction like that yet, because they know that the job that they have now is probably not a job they will have for life, and probably later on they will get a better job. So maybe for them it doesn't really work so strongly as causal mechanism, or maybe even not at all. So this causal mechanism that connects differences in income to differences in satisfaction of government. Yeah, so that's the idea, that these causal mechanisms depend on certain conditions. So when we want to statistically analyze that, that implies that we can somehow observe these conditions as variables. And if we can do that, we can do what is called a moderation analysis, because if we translate this idea of conditionality of our causal mechanisms into effects that we can statistically estimate, then we have to translate them into so-called moderation, or often also referred to as interaction effects. So that's great, because that means that we can go a step further in testing our theories, because then we have more things that we can test our theory on. Not only is there an effect implied by the causal mechanism, but also is it true that that effect is stronger or weaker, depending on what the theory tells us about when the causal mechanism operates stronger or weaker. Yeah, so that gives us extra room to falsify our theories. Another thing that we can often do is, because of course these causal mechanisms basically give us a story about why there is a connection between X and Y. So why does more income lead to satisfaction with government? And in the example I just gave you, well, the theoretical reasoning was based on the idea that more income leads to more satisfaction with life overall. More satisfaction with life overall leads to more satisfaction with, government, like with political representation, with political institutions. And here we have a nice example of a part of our causal mechanism that we can actually observe, because life satisfaction is actually a variable that's included in the European Social Survey. So we could include that variable in our analysis and could take a look at, well, is it really the case that this income effect works through life satisfaction? So we can analyze this causal mechanism further by seeing, well, are there intermediate variables, so these so-called set variables that go in between X and Y, and can we observe them? Because if we can observe them, then we can test this entire path that goes from X to Y via these third Z variables. Yeah, and again, this gives us more room to test and potentially falsify our theory, because then we can see, well, is it also, it's not just the case that we see the expected effect of X and Y, but this is also because of the theoretical causal mechanism that we expect to lead to this effect. And this is the so-called mediation analysis. Yeah, so these are two different terms that look a bit alike, but they are about different things. Moderation analysis is about analyzing the conditions under which causal mechanisms operate. And mediation analysis is about analyzing the path the pathway that is being created by the causal mechanism. So this the intermediate steps in that pathway. Yeah. So a nice way to remember that is moderation. Well, there is this MOD part, which is also in the word modify. So you can remember that as effects that are being modified by other variables. And mediation analysis, well, it's it's like in the middle, right? So like mid. So that's also a nice heuristic if you want to keep them apart. So mediation is about what's in the middle, what goes in between, and moderation is about what modifies relationships. Yeah, and this will become more clear if we discuss how to actually do that, of course. Yeah, so let's start with moderation analysis, which is, as I already mentioned, often also referred to as interaction analysis or interaction effects, if we're talking about the effects that we're estimating in this way. So conceptually, what are we talking about? We're talking about, okay, we have some variable, some X variable, for which we say, okay, that has an effect on our dependent variable because of some causal mechanism. But we also know, based on the theory, that there are certain conditions under which this effect should be stronger or weaker, and we can measure those conditions with some second X variables and X2 variable. So if we want to put that into a conceptual model, we draw an arrow from X to Y, from X1 to Y, to indicate that this is the basic relationship that we are interested in. But we also know theoretically that it should be the case that that relationship itself is actually affected by a third variable, an X2 variable. So we draw an arrow running from that X2 variable to the arrow that runs between X1 and Y, indicating that this is not an effect on any of the variables, but it's an effect on an effect. So it is a third variable that modifies the relationship between X1 and Y. So in that third variable, we refer to that as the moderator variable because it moderates the relationship between the independent variable that we start out with. Yeah, so and the dependent variable. So interaction or moderation hypothesis will generally be formulated something like the effect of our x variable on our dependent variable will be stronger or bigger the higher the value of this moderator variable, this x2 variable is. Yeah, so then we have an hypothesis where we basically know that if our theory is correct, and it should be the case, that the higher the value on our moderator value is, so the higher the value is on our x2 variable, the stronger or the bigger the effect on of our x1 variable on our dependent variable should be. So this is a positive interaction hypothesis. It could of course also be a negative moderation or interaction hypothesis. So if the theory tells you no, it's actually supposed to get weaker, this effect of x1 on y, if the value on x2 increases, then these hypotheses will be something like the effect of x1 on y will be smaller or weaker the higher the value of x2 is. Yeah, so both of these situations are possible. You can have positive interaction hypothesis or negative interaction hypotheses. So how do we do that in a regression model? Well, this is the basic shape of a multiple linear regression model where we have also included an interaction term. So this is referred to often as an interaction model. So notice that this is basically just like all the regression models that we saw already. So it's a multiple linear regression model. So we still have a dependent variable y that we observe for each case I. And we have a linear relationship, so we have an equal sign, after which we see, well, we have a constant of b0 plus a b1 x1 term plus a b2 x2 term plus, and this is new, a b3 x1 times x2 term plus whatever else you put in your model. Yeah, so x1 refers to the moderator variable, so the independent variable, x2 refers to the moderator variable, and this x1 times x2 again refers to the same independent and moderator variable. So we now see that x1 is twice in our model. It's here with this b1 coefficient and it's here with this b3 coefficient, and x2 is in the model twice. It's here with the b2 coefficient and it's here in this extra term where we have a multiplication with the x1 variable going on. And of course, whatever else you have in terms of control variables, you can also include in that regression model. And we still have, of course, an error term indicating that part of the observed value in our dependent variable that we are not able to explain with that model. Yeah, so let's go over that step by step. So let's start with this weird new term that we added to the regression model, where we have b3 that's multiplied by x1 for each case times x2 for each case. So the value on x1 for each case is being multiplied by the value by x2, and that is being multiplied by the regression coefficient b3. So this part of the interaction model is referred to as the interaction term, because this is really what makes it an interaction model, including this extra term. So what does this term represent? Well, it's the multiplied values on x1 and x2 for each case I, and that is then being multiplied by our regression coefficient b3. And then in the interaction model, we would call the effects of x1 and x2, yeah, which we have already in the model. We would call those the main effects. So we have a main effect for x1 and we have a main effect for x2, and we have an interaction term where both x1 and x2 are multiplied with each other, and then we have a separate b3 coefficient for that interaction term. Yeah, so what does the b1 coefficient tell us in this model? Well, if you think about this abstractly, what it tells us is basically it shows us the effect of x1 if x2 is 0. Why is that? Well, think about what would happen if x2 takes the value 0. So if our moderator variable takes the value 0, well, then this term would be b2 multiplied by 0. Multiply something by 0 and you get 0. So you can forget about this. You can drop this from the equation. And this term would also be, well, x2 multiplied by x1. Well, if x2 gets the value 0, then this is 0 multiplied by whatever value we have on x1, which of course again multiplies something by 0 and you get 0. So this would then always result in the value 0. And then we would multiply our coefficient b3 by 0, which means that this would also result in a 0. So we could both basically drop all of this from our regression model. In other words, what we then have is only a b1 coefficient for x1 for our independent variable x1. So the b1 coefficient tells us what the effect is of x1 if x2 is equal to 0. Abstractly, yeah, of course, again, don't panic if you don't fully understand it yet. Of course, we're going to go over concrete examples and you'll get to practice with all of that stuff. Yeah. The same reasoning can be applied to the B2 coefficient. Well, what does the B2 coefficient in an interaction model tell us? So the coefficient for the main effect of x2, well, it shows us the effect of x2 if x1 takes the value 0, because again, what would happen if x1 takes the value 0? Well, then this part of the regression model would be multiplied by 0, so that would drop out of the equation, and this part, this interaction term, would be multiplied by 0, so it would drop out of the equation. Yeah, so that's the what the main effects in the model tell us. And then the most interesting part will be the B3 coefficient. Yeah, so this is the coefficient of the that gives us the interaction effect, because it's the coefficient for our interaction term. And that tells us by how much the effect of x1 changes with a 1 unit increase in x2. So how much does the coefficient, the slope coefficient that represents the effects of x1, change with a 1 unit increase in x2? Yeah, so now we are letting the coefficient, the slope coefficient of x1, we are letting that depend on the values of x2, because we have a moderation interaction model where we say, well, we expect that the effect of x1 depends on the value of x2. At the same time, it also has a different interpretation, because we can also interpret this regression coefficient B3 as telling us how much the effect of x2 changes with a 1 unit increase in x1. Because we are just multiplying x1 and x2, so both of these interpretations are completely identical. From a mathematical standpoint, there is no difference. I mean, it's exactly the same model. So both of these interpretations are completely correct. So that's exactly because that's the underlying model is exactly the same. So which one of these interpretations you choose as a researcher depends on which one of these two variables, so x1 or x2, you consider to be the moderator variable. So if x2 is your moderator variable, as we started out with in this conceptual model, then we would follow the first interpretation. So we would follow the interpretation of this B3 coefficient tells us how much the effect of x1 changes with a 1 unit increase in x2, because x2 is the moderator that modifies the relationship between x1 and our dependent variable. But if our theory would have suggested, no, it's actually x1 that's the moderator, and we have it's actually about the effect of x2, then we can just interpret B3 as representing how much the effect of x2 changes with a 1 unit increase in x1, because again, mathematically, both of these things are completely equivalent. So it really depends on your theory which one of those interpretations you use. So which one of those variables do you consider to be the independent variable, and which one do you consider to be the moderating variable, the moderator? Now, before we go to a concrete example of that, I want to take a little bit of a sidestep because it's going to come in useful when we do this moderation analysis. So I want to talk a little bit about rescaling our variables, and specifically one specific way of rescaling variables, which is sometimes referred to as centering your variables. So what do I mean by that? Well, often if you do regression models and also many other types of statistical analysis, it can be quite useful to rescale, so change the scale of your x variables by changing the location of your zero value on that scale. So changing which value is on your x variable is represented by the number 0. And this often can be quite useful. So for instance, one way you could do that is you could shift your scale of the x variable in such a way that the zero value on the new variable that you create is identical to the lowest observed value on the original scale. So you could say, I'm going to create a new variable in my data set, which is the original variable minus the lowest observed value on that variable. Yeah, so for instance, let's say you want to rescale age, for instance, and let's assume that the youngest person in your data set is 18 years old. You could create a new variable for age, where we are changing what the zero value represents by saying, well, for this new variable, I'm going to compute that by taking the original observation of age for each person and subtracting from that the lowest observed value in my data set, which is 18 years. So for each observation of age, the new variable would be the age of the respondent minus 18, because that would be then the lowest observed value on age. So all you're doing in that case is basically shifting what the zero represents on your x variable. Yeah, because that means that on your new variable, the value 0 will be the lowest value on the original variable that you observed. So if on your original variable the lowest observed value was 18, so the youngest person in our data set was 18, then that person will get the value 0 on our new x variable, yeah, with this transformation, because we changed the location of the 0 value. Now, why would you want to do that? Well, one reason that might be useful to do is because it helps with interpreting the constant or intercept in the regression equation. What it doesn't do, it doesn't actually change the regression coefficient that you would find for your x variable, because we have a linear regression model, right? So it doesn't matter where our y-axis, our regression line intersects with the y-axis. The effect is always the same. So it really doesn't matter where that intersection is taking place. But it does matter for our B0 coefficient, so for our constant, right? Because what is the constant? It is that predicted value that you would get if all the other x variables in the model take the value 0. And we already saw with the examples that we used so far that it's quite annoying if you have a constant value that refers to cases that actually cannot exist in your population. Yeah, so for instance, we saw that we have these regression models where we included, for instance, age and income in the regression model. We just used the original variables, and then we estimated regression models. We got a constant value, some value that we had to interpret. Okay, this is the predicted value on satisfaction with democracy for a person that is 0 years old and scores a 0 on the household income measurement, which is of course completely impossible because such a person cannot exist. Well, one thing is, 0-year-old persons would be quite hard to get to answer a survey, questionnaire survey, and probably also not the population you actually want to make inferences about. Yeah, probably you want to make inferences about adults. It's completely impossible, of course, also for somebody to score a 0 on the income variable that we're using in the ESS, because the lowest possible value is actually a 1, indicating that you're in the first decile of household income. So 0 is a nonsensical value. Yeah, so that's annoying. If you just use the original scales of the variables, you get an intercept that you know how to interpret, but the interpretation is not very useful because it refers to cases that can't actually exist. So by shifting rescaling your x variables, you can make sure that you have a constant that you can meaningfully interpret. Yeah, so for instance, by using this trick of shifting the 0 value of all your x variables to the lowest observed values, we now have a much more interpretable coefficient. Yeah, so we suppose that we would have a multiple regression model with age and income, and we would first rescale them in such a way that 0 on the age variable now refers to the youngest observed person in the data set, and 0 on the income variable now refers to the persons with the lowest observed income. Yeah, so the persons that would, for instance, be 18 years old on the original variable of age, and that would score a 1 on the income variable. So great, if we do that, so now our intercept actually refers to those persons, so the predicted value for the persons that are 18 years old and in the first decile of household income. So that's often very useful to do this rescaling. Again, it doesn't matter for your estimated coefficients. They will stay exactly the same because we have a linear regression model, but it does make this interpretation of the constant more meaningful. So that's a nice trick that you can use if you want to help yourself and your reader with interpreting your results. Now there is a different way of rescaling your variables that's quite common, and that is mean centering your x variables. So what's the idea of mean centering? Well, the word mean is included, so probably this has something to do with the mean value. Okay, so what do we mean specifically? It's the idea that we shift the scale of our variable, of our x variable, in such a way that the value 0 represents the mean value. So we make a new variable in our data set that is based on the old x variable, and we do that in such a way that a value 0 on that new variable, so on that new scale that we're using, is identical to the mean value on the original scale of that x variable. So we have a mean-centered version of our x variable. That means for each case, we are going to assign that variable the value that is the observed value on the original scale minus the average, minus the mean value on that variable. Yeah, so how can we now interpret this new scale? Well, we can interpret that literally as deviation scores, right? Because values on this centered version of our x variable now represent how far removed each case is from the mean on that variable. So these are really just deviation scores. Yeah, again, all we did is we shifted the value of 0. So we changed the location of the value 0. So in other words, it's still the case that it doesn't matter for your regression coefficients. They will stay exactly the same. But it has some other nice consequences. Yeah. 0 on this new centered variable would be identical to the mean value on the original variable. Yeah, so if a case on our centered variable would score exactly the mean value on h, and we would create a mean-centered version of h, then that case would score a 0 on the new mean-centered version of h, and then all people that are older than the mean age will get a positive value on that mean-centered version of h, and all the people that are younger than the mean age will get a negative value on that centered version of h. Yeah. So why would you want to do that? Well, one situation where it's super useful is if you do interaction models. So if you do moderation analysis. There are also lots of other situations which you probably will encounter in later courses where it can be super useful to use mean centering. But today we're talking about moderation effects, and this is typically a situation where I would really advise to mean center the x variables that are involved in the interaction. So those that you put in the interaction term, at least to mean center those variables. So center those variables on their mean values. Well, why would you want to do that? Well, it doesn't actually matter for the interaction effect that you estimate. So this B3 coefficient for the interaction term will stay the same regardless how you scale your x variables that are involved in the interaction effect. But what it will do is it will make the main effects for those variables much easier to interpret. And that is quite useful because these models get quite complicated. So it's super useful if we make sure that we make them as easy as possible to interpret. Yeah, and so mean centering is super useful for that. The second reason why it's quite useful is because you might want to look at things like VIF values, yeah, the variance inflation factors, or equivalently look at tolerance values to see, well, do I have a problem with multicollinearity? Yeah, we already learned how to do that and what it means. And the thing is, if you have interaction variables, then you are including the same variables twice in your model because you have them included as main effects, but you also have included them in the interaction term. And because the interaction term is just multiplying the values of those original two variables with each other, it also means that the value of that interaction term is going to depend on the value of the original variables because it's just a multiplication of those values with the values on the other x variable. So by definition, your interaction term and your main effects are going to show some degree of dependency. So some correlation is going to be, by definition, is going to exist between them. And this is going to blow up your VIF values. So it will look like you have a terrible problem with multicollinearity. And this is usually not because you actually do have a problem with multicollinearity. It's just a consequence of this dependency and how the VIF values and the tolerance values are calculated. If you use the original variables, this problem is prevented if you mean center your variables. Then you won't get this incorrectly blown up values for your VIF values. Yeah, so this is basically a mathematical trick so that you can still use VIF values like you would normally do. So just look at the VIF values. Are there any super high VIF values? And that will indicate a problem with multicollinearity, instead of having to worry about, well, but is it now because I have an interaction term, or is there really some multicollinearity going on? So it helps with this kind of false increase in those VIF values, or correspondingly a false decrease in the tolerance values, because again, tolerance and VIF is basically just the same thing expressed on a different scale. Yeah, so that's those are two reasons why you might want to do that: interpretation, and also it helps if you look at stuff like VIF values. So if you assess multicollinearity. So okay, that was a lot of super abstract exposition, which is of course necessary. But yeah, by now you probably are completely fed up with me already. So hang in there. Let's look at a concrete example to make it a bit more tangible. So let's say I have a theory that implies a causal mechanism that connects religiosity to satisfaction with government. So based on that causal mechanism, I formulate the hypothesis that the more religious people are, the more satisfied they will be with their government. Okay, so far so good. We're just talking about a straight up direct effect of religiosity on satisfaction with government, which we expect to be positive based on our causal mechanism. So far, okay. We don't need an interaction model. We have enough on with our normal multiple linear regression models. But now let's suppose that our theory also tells us that this mechanism that connects religiosity to satisfaction of government is conditional on age. So that how strong this mechanism works, this theoretical mechanism, depends on how old people are. And maybe based on our theory, we say, well, it should also be the case that the older people are, the stronger that effect of religiosity on satisfaction with government will be. Yeah, for whatever theoretical reasoning. You could say, well, if the theory is correct, then it should be the case that this religiosity effect, this positive effect of religiosity on satisfaction with government, you should see that more with older people than with younger people. Yeah, so you're expecting a positive interaction effect where age is a moderator and religiosity is the independent variable, and we expect that the effect of religiosity increases as people get older. And of course, if we want to test this hypothesis, then we do need an interaction model, because this is clearly an interaction hypothesis, because we now say that the effect of religiosity on satisfaction with government itself depends on a third variable, on the value of a third variable, namely age. Yeah. So how would I go about doing that? Well, I did it with some old European social survey data. And so the first thing I did is, well, I said, well, I have age and religiosity. And religiosity is my independent variable and age is my moderator variable. So both of these variables are involved in the interaction effect that I want to estimate. So I'm going to mean center those variables first. So first step of then, of course, is, of course, well, if you want to mean center, you need to know what the mean is for each variable. So I looked up the mean value of age in my data set, and it turned out to be 51.67. And I looked up the mean value on religiosity in my data set, and that turned out to be 4.245. Right, so now I know what the mean of age is and what the mean of religiosity is. So now I can create two new variables in my data set that are mean-centered versions of age and religiosity. So for the age, for the mean-centered version of age, I calculate the observed age for each respondent minus the average mean age of 51.67. And for the mean-centered version of religiosity, I take the observed religiosity on the original scale for each respondent, for each person, minus the mean value of 4.24. So that would be then the values of my mean-centered age and religiosity variables. Then the third thing I need to do is I need to create my interaction term, which means that I have to multiply the values on the two variables that have a part in that interaction effect. So religiosity, my independent variable, and age, my moderator variable. I need to multiply the values that I observe for these two variables. So I created a mean-centered version of those variables, and now I'm going to create a third new variable in my data set, the interaction variable, where I'm multiplying each mean-centered value of age with each mean-centered value of religiosity. Yeah, so that's now my interaction term. And then I can estimate my regression model, and I need to include the age variable. I'm using, of course, the mean-centered version of age. For the main effect of age, I'm going to include the religiosity-centered variable for the main effect of religiosity. And I'm going to include the interaction variable of age multiplied by religiosity for the actual interaction effect, for the interaction coefficient. Yeah, so I need to include all three of these things in my interaction model. So age centered for the main effect of age, religiosity centered for the main effect of religiosity, and the interaction variable age centered times religiosity centered. And of course, as always, also think about potential control variables that you might want to include in your model because you want to adjust for those differences in those other variables, because you want to get better estimates of the causal effect, and you think that there are potential confounders that you want to control for. So I did this, and I estimated a fairly simple model. Didn't put too much thought into it. Just wanted to have a nice example for you. So this is the model that I estimated. I'm only showing you the coefficients table because everything else is the same as with a normal regression model. But the coefficients table, now that's where the interesting stuff is happening. So I have age-centered that I included. I have religiosity-centered that I included. I also included household income, and I included the interaction term in my model. So why did I include income? Well, I didn't really think too deeply about control variables, but I just figured, maybe adjust at least for differences in income. Yeah, so we have at least one control variable in there. Yeah, again, so just to have an example, no deep thought went into that, but just to show you that you can just include control variables, and you should include control variables as well in your model. Yeah, so income just as a control variable, main effect of age. That's great, because we use the mean-centered version of age. The coefficient we find for that is minus 0.003. is actually not that difficult to interpret. Because, well, what are the main effects? Remember, the main effect in interaction model is the effect of that variable if the other variable that's involved in the interaction is 0. So in this case, we change the 0 values to correspond to the mean values of age-centered and religiosity-centered. So how can I now interpret this age main effect of minus 0.003? Well, it's the effect of age for people that have a mean value on religiosity, so people that are averagely religious. Because for people that are averagely religious, that have a mean value on religiosity, the religiosity-centered variable gets the value 0. So for those people that have an average amount of religiosity, and this coefficient gets multiplied by 0, and this coefficient gets multiplied by 0. In other words, we don't have to worry about them anymore. All we have to worry about is this main effect of age. Yeah, and this is the reason why mean centering is really nice if you have interaction models, because then you can also directly interpret the main effects as, okay, this is the effect of that variable if the other variable in the interaction term is at its 0 value. And of course, because you're picking the mean here as a 0 value, that's quite nice, because that basically reflects where most of the cases would be located, because it's the center of the distribution of those of that other variable. Yeah, so that's nice, because that helps us to interpret these main effects. Conversely, we can now also interpret the main effect of religiosity as well. Okay, this is the effect of religiosity for people that have the mean value on age, so people of an average age. Again, because of the exact same reasoning, we use the mean-centered version of age in the interaction model. So that means that For people that have exactly the mean value on age on the original age variable, they get a 0 on the age-centered variable. So for them, this age main effect would be multiplied by 0 and just becomes 0 and drops out of the equation. And also the interaction term would be multiplied by 0 and drops out of the equation. Yeah, so that's nice that we now have a nice, more intuitive interpretation of the main effects. Of course, the most interesting thing is probably going to be the interaction effect. So this estimated interaction coefficient of 0.002. So in this case, we find that the p-value that's associated with that is 0.026. So that's lower than our standard alpha level of 0.5. So we could say, well, it's quite unlikely to find this interaction effect if there in fact is no interaction effect going on in the population at all. So we can reject that null hypothesis in favor of the alternative hypothesis that there is an interaction effect, in this case a positive interaction effect, because we find a positive coefficient for the interaction term of 0.002. Yeah, which basically means that this does indicate that the effect of religiosity becomes stronger as age increases. So the older people are, the stronger our religiosity effect actually is. More specifically, what does the 0.002 exactly tell us? Well, it tells us that for every year a person is older, the slope coefficient of the religiosity effect increases by 0.002 points. Because that's what our interaction term captures. It captures by how much does the slope coefficient for our independent variable increase or decrease if our moderator variable increases by 1 unit on its scale. In this case, our moderator variable was age, so the scale was in years. So that tells us that for every year older a person is, the slope coefficient of the religiosity effect increases by 0.002 points. Yeah, notice that now we don't really have a model where we have an effect of religiosity anymore. Now we have a model wherein we capture that the religiosity effect itself, what that actually is, so what the slope coefficient of the religiosity effect is, so how steep the regression line is, that actually depends on differences in age. And now we actually captured that in our model. Yeah, so that's how to interpret these interaction coefficients. Now, this is still quite it's not complete, because now all we know is how the slope coefficient changes, but we don't really fully understand yet from what to what it does change in our sample. That is something we'll take a look at in the B lecture of this week to get an even firmer grip on what exactly do these interaction models tell us. But for now, it's enough to understand that what does this interaction term itself tells. It tells us that by how much the slope coefficient of our independent variable changes for 1 unit increase in our moderator variable. So in this case, we find a positive interaction effect that would be statistically significant at the conventional alpha level of 0.05. So we could say, well, this supports our hypothesis that it is indeed the case that the older people are, the stronger the effect of religiosity on satisfaction of the national government is. So that's for moderation. For now, of course, you will practice in the assignment, and then in the B lecture we'll go, as always, a bit further and a bit deeper. And it will come, so don't panic if you don't get it immediately, because these are quite complicated models to understand. So let's take a look first now at the other thing that we need to discuss, mediation analysis. So what is mediation analysis? Well, we discussed that this is basically analyzing the pathway that connects X to Y. So the causal path that is the reason why there is an effect of X on Y. Yeah, so we can start out with, again, we have some theory that tells us that some independent variable X has some causal effect on a dependent variable Y. But our theory might also tell us how, and should tell us, why that is the case. So what is the causal mechanism that connects X to Y? And we might be able to measure part of that causal mechanism because we observe some of these variables that go in between X and Y. So in that case, our theory tells us exactly why we expect that original association between X and Y to be there, and tells us what it actually results from. Yeah, so that's what mediation analysis tries to do. It tries to figure out to what extent that is actually the case. Yeah, so then this third variable that we have, we call it a mediator variable. So it goes midway in between X and Y. So it's part of the causal mechanism that connects x and y. And we call this effect of x on y that runs through z, so that goes through the effect that x has on z, and that z then has on y, we call that an indirect effect. Yeah, because it goes indirectly through that mediator z variable, and we call whatever effect we have left of our x variable on our dependent y variable the direct effect, because of course that might be a part of the reason why x has an effect on y, that mediator variable, but there might be other reasons why x has an effect on y, so those would be captured by the remaining direct effect that we have of x on y. So mediation hypothesis generally take the shape of something like the effect of x on y can be explained by the effect that x has on z, or at least partially explained, because often we realize that there might be other reasons why x has an effect on y, but at least we know one theoretical mechanism that connects x and y. So then we can say that the effect of x and y can at least partially be explained by the effect of x on z, by this indirect effect. So that's the general shape of mediation hypothesis. They will generally be formulated something like this. So how can we test that? Well, if we want to test whether there is this mediation effect, we actually need to estimate 4 different effects to properly do that. At least in the way that I'm showing you, which is sometimes referred to as the Barron and Kenny method of doing mediation analysis, because those were the people that kind of, I wouldn't say invented, but solidified this way of testing mediation effects. There are also other ways, which I'll discuss at the end of this lecture, which go a little bit more complicated, but this is a nice, useful way to start with mediation analysis. So what do we need for testing this mediation analysis? We need 4 different effects. Well, first we need to find out what is the effect of our independent variable on our mediator variable. So we're going to call this the path A. Just so that we know what path we are talking about, because now we're going to talk about multiple arrows running in between different variables. So the effect that x has on z, so the effect that our independent variable has on our potential mediator variable, this is something we need to find out. That is something we need to estimate. How big is that effect? And we need to find out, well, how big is the effect of our mediator variable on our dependent variable? So this is also something we need to find out. We need to estimate what is the effect of z on y, and we are going to call this the B path. So the B part of the path that connects x to y. So we have an indirect effect that is basically in 2 parts, the A part from x to z and the B part from z to y. We also need to know what the original effect of x on y was, and we're going to call that the C path. So that is the effect of x and y before we took into account the mediator variable. So just the original relationship, the unmediated relationship that we started out with. So we're going to call that the C path. And we're going to call this the simple relationship. So we are not taking into account the mediation yet. In that simple relationship, we're only going to look at, well, what is the effect of x on y? And then lastly, we also need to know, okay, what then is the effect of x on y once we took into account this indirect path through the mediator? So what is the remaining direct effect of x on y? And this is what we are going to refer to with the C apostrophe, because it refers to the same effect. It refers to the effect of x on y, but C is for the original effect, where we didn't take into account the differences on the mediator variable, whereas C apostrophe is for the remaining direct effect that we have left once we do take into account differences in the mediator variable. So once we do take into account the indirect effect running through the Z variable. So we call this overall, we call this the mediated relationship between x and y. So these are 4 effects that we actually need to estimate in order to test mediation and mediation hypothesis. The nice thing is, even though it's 4 effects, we only need 3 models that we need to estimate to get estimates for these A, B, C, and C apostrophe effects. Well, the first thing we need, of course, we need to estimate the effect of x and y without taking into account the mediation, so the simple relationship. So get the value for the C effect. And for that, we can just use the normal regression model where we take as our dependent variable, our Y variable, and as an independent variable, we can use our X variable. Yeah, so this is just a standard regression model like you are used to. But this will tell us at least one thing. It will tell us the value of C because that will be given by our regression coefficient B1. The second thing we need to do is we need to also find out, well, what is the effect of X on Z. So we need to find a coefficient that represents the A path. And for that, we're actually going to change what variable we are taking as the dependent variable. So rather than using the dependent variable that we are actually interested in, we're going to use the mediator as a dependent variable, so the Z variable. So the Z variable, we're going to also estimate a regression model for that, and we're going to take our independent X variable as an X variable in that model, because then we know, okay, this model estimates the relationship between X and Z. It tells us what the effect is of X on our Z variable, on our mediator variable. So the regression coefficient B1 in this model is going to tell us what the A path is, so what the effect of X on Z is. And then finally, we need to estimate a third model, where again we are switching back to the dependent variable that we actually want to say something about, so the real dependent variable that we're interested in theoretically. And now we're going to again estimate a regression model, and we're going to include both X and Z, so both the independent variable as well as the mediator variable in that model. So now we get a new effect for our X variable on our dependent variable Y. And this is the effect that this B1 coefficient in this third model is the effect of our X variable on a dependent variable controlling for or adjusting for differences in our mediator variable. In other words, it is the effect of our X variable on a dependent variable that is left once we have taken into account differences on our mediator variable. So it is the remaining direct effect in our mediated relationship. So the B1 coefficient in this third model gives us the value for the C apostrophe path from X to Y. So the direct relationship between X and Y in the mediated model, basically, where we are taking into account differences on the moderator variable, and the B2 coefficient in this model, so the coefficient that we find for the Z variable for the mediator variable, tells us what the effect of the mediator on our dependent variable is. So it gives us the value for the B part of this path, of this causal pathway. Yeah, so we have 3 regression models that we need to estimate to find 4 different effects. C, the original relationship between X and Y, C apostrophe, the mediated effect that we are left with, so the direct effect that's left of X and Y once we take into account differences in the mediator. A, the effect of X on the mediator, on the Z variable, and B, the effect of the mediator, the Z variable, on our dependent variable. Yeah, so 4 effects that we need to find, 3 models that we need to estimate, and 4 conditions that we need to have in place in order to say our mediation hypothesis is supported. So there is 4 conditions that should be satisfied if you want to say, yes, we can indeed say that the mediation hypothesis that we have is indeed supported by the data. So what needs to be the case? Well, first thing, the effect that you start out with should itself already be, well, significant. There should already be an effect, because if there is no effect to start out with, then it doesn't really make sense to talk about a mediation effect, because mediation implies that there is an effect that we are able to explain by referring to a third variable, a mediator variable. So there is a causal mechanism that leads to an effect between X and Y. Well, if there isn't one to start out with, then you can stop already with your mediation analysis, because basically then there is no effect that you are able to explain with the mediator variable. So there should be some kind of effect of X and Y where we can say, well, I can confidently generalize this to the population. There seems to be something going on with an effect of X and Y on Y. The second condition that needs to be fulfilled is that there should also be an effect of X on Z. So the A path should also be statistically significant in that sense. Yeah, so you should actually find that it is indeed the case that your independent variable actually has an effect on the mediator variable, because that is implied by the causal mechanism, right? That there is this indirect effect, and that means there needs to be this A path in the mediated relationship. So that should also be significant. And of course, the B path also should be significant. So the effect of your mediator variable on your dependent variable should also show such a small p-value that you are willing to say, well, it's quite unlikely to find this if there isn't some effect going on in the population. So also this should be, this B effect should be significant. And lastly, well, it is implied in this mediation analysis that the original effect that we started out with from our dependent variable and our independent variable, so the effect of x and y, to some extent can be explained by differences in the mediator variable, so that there's this indirect effect through the mediator variable, which implies that the original effect that you started out with should decrease once you take into account differences on the mediator, because you're partially explaining away that original unmediated relationship, so that simple relationship between x and y. So the effect, the coefficient that you find for the C apostrophe part in model 3 should be smaller. So the value of that coefficient should be smaller than the original coefficient that you found in the unmediated, in the simple relationship. Yeah, so if it's a positive coefficient, that should be a larger number, a smaller number that you find for C apostrophe than for C. And if it's a negative coefficient, then the original C path should be more negative. So it should be a larger negative number than the C apostrophe path. So that should move closer to 0, basically, because that indicates that we are reducing the size of the effect of x and y if we take into account the mediator variables. In other words, that suggests that the mediator is indeed responsible for part of that original effect. Yeah, and only if all of these 4 necessary conditions are established would you say, well, okay, that supports our mediation hypothesis. Again, this is the so-called Baron and Kenny method. There are other more sophisticated methods of doing that, but for now it's good that you learn this method already. Yeah, so again, this was the abstract. Let's go into a concrete example. Let's say I have a theory that tells me that the higher people's income is, the more satisfied they will be with their government. So that might be my main first hypothesis, but let's say that my theory also tells me, well, the reason why this is the case, so the causal mechanism is behind that, is because more income makes people happier. Yeah, so the more income people have, the more happy they are overall. And happy people are just happy with everything and satisfied with everything. So my theory specifies a causal mechanism that runs through those differences in happiness. Yeah, that basically says, well, the effect of income on satisfaction with government is partially explained by the effect that income has on people's happiness. And of course, yeah, great. If my theory shows me that this should be true and I can actually observe happiness because I measured it somehow, then I can also test the mediation hypothesis about that to see, well, is this also true? Can I actually also see this happening in my data? Yeah, so let's say I have this theory and actually did some mediation analysis on that based on some old European Social Survey data again. So what did I do? I first estimated the model 1, so the simple relationship between income and satisfaction with government. So I just included income as an independent variable here, and I found a regression coefficient of 0.167 and a associated p-value that's quite small, so smaller than 0.001. So what can I say now? Well, I can say that the first condition that needs to be satisfied for there to be a mediation effect is in fact satisfied, because I find that the simple relationship between income and satisfaction with the national government is fairly statistically significant. Yeah, so I find a super low p-value, so it's quite unlikely to find this effect if in fact there is no effect of income on satisfaction with the national government in the population. So I can reject that null hypothesis, so my first condition is in this case fulfilled. So I already know what the simple relationship looks like. I know that the effect of income on satisfaction of government is given by this regression coefficient of 0.167. Great. Now, of course, I also need to know, well, what is the effect of income on happiness? Now, there is this nice variable in the European Social Survey that asks people, well, how happy are you? I think on a scale from 1 to 5, where a higher value indicates more happiness. And, well, then I just took that as a dependent variable. Yeah, so notice now I switched dependent variables to happy, the variable measuring happiness, and I still use income as the independent variable to see what is the effect of income on happiness. And I find a regression coefficient of 0.149, and again with a really small p-value of smaller than 0.001. So again, here I could reject the null hypothesis of no income effect in favor of the alternative hypothesis that there is some positive effect of income on happiness. Yeah, so the second condition is also fulfilled. Our A path in the mediated model is statistically significant. So now I can say, well, okay, this effect of income on happiness, that is represented in our estimates by the regression coefficient of 0.149. That tells me the effect of income on happiness. So for every one decimal increase in household income, the predicted value on happiness increases by 0.149 points. Cool. And then I estimated the third model, where again I switched back to satisfaction of the national government as a dependent variable, but now I'm including both income as well as happiness as X variables in my model as variables on the right hand side after the equal sign. So this is the model that I found, that I estimated, and hey, looking at the effect of happiness, I find a regression coefficient of 0.189, and I find also a p-value that's super small, indicating that we can reject the null hypothesis for this square regression coefficient. So there seems to be some positive effect of happiness on satisfaction with national government in the population, adjusting for differences in income, controlling for differences in income. So also the third condition is fulfilled. We see that the B path is also statistically significant, so there seems to be an effect going on of happiness on satisfaction of the national government, and that's given by the regression coefficient of 0.189. So for every 1 point increase on the happiness scale, the predicted value on satisfaction with the national government increases by 0.189 points, adjusting for differences in income. And I also see that my income effect that I now found has now the value of 0.139. So the direct effect of income on satisfaction of the national government, adjusting for differences in the mediator happiness, that effect now is 0.139. So for every 1 decimal increase in household income, the predicted value on satisfaction of government increases by 0.139 points, adjusting for differences in happiness. So putting all of this together, we started out with a simple relationship of income and satisfaction of government that we found the coefficient for that we found was 0.167, and then we did the model 2 that showed us what the effect of income on happiness was, and it turned out to be 0.149. And then we had the third model that showed us what the effect of happiness on satisfaction of government was estimated to be, and it turned out to be 0.189. And it showed us what the income effect is that we have left once we take into account difference in happiness, so the direct effect of income, and that turned out to be 0.139. So in this case, we see that the C apostrophe, the direct effect of income once we take into account difference in happiness, actually has a smaller value than the original income effect that we started out with, because 0.139 is smaller than 0.167. It's not a lot. It's not like happiness explains the entire income effect. We still have a quite sizable remaining income effect. It's also still statistically significant at conventional levels. But we have been able to explain some of that original income effect with referring to differences in happiness. So in this case, we could say, well, all the 4 conditions are supported. So in this case, our mediation hypothesis is supported. The effect of income on people's satisfaction with the government can at least partially be explained by the effect that income has on people's happiness. So that's great. That tells us a lot about who is happy and why, and how that relates to, well, how people feel about politics. So in general, we have this this mediation model where we have an X variable, our independent variable, a Z variable, a potential mediator, and a dependent variable Y. And we have the A times B indirect effect and the remaining C apostrophe direct effect. So the direct effect is C apostrophe. That's the direct effect of X and Y that remains once we take into account difference on the mediator. And we also have an indirect effect, and you can actually calculate what exactly that indirect effect is by just multiplying the 2 coefficients that you get. So the coefficient you get for A multiplied by the coefficient that you get for B gives you the indirect effect of X and Y that runs through Z. So in other words, you can interpret this A times B as how much the predicted value on Y increases for every 1 unit increase in X through the effect that X has on Z. So it's telling you how much the predicted value on the dependent variable increases with a 1 unit increase in your independent variable only through that indirect path, so through that mediator variable. Yeah, so that's nice. So now you also know how to interpret this effect. So again, in this case, we could say, this, you might take this even further. You might also want to test whether this indirect effect, so this A times B, whether that's statistically significant. Yeah, because your mediation analysis implies that this path in its entirety is statistically significant. We know that this path was, in our example, we know that this path was, but we don't yet know about this A times B, so this entire path taken together. Yeah, because then you would somehow need to have one single way of testing that. So that would be even greater. If you want to go even further in supporting your mediation hypothesis, you would want to say something about the null hypothesis that this indirect effect in the population is 0 against the alternative hypothesis that it is not 0, that's larger, or that it's smaller than 0. Going back to our example, I'm first going to bring back, well, what was for the immediate relationships that we found. It was this, right? So this is exactly the same that same picture that we already saw. So now we know how we can calculate the indirect effect of income through happiness on satisfaction with government. It's 0.149 multiplied by 0.189, which works out to be 0.028. So now we know that for every 1 decile increase in income, the predicted value on satisfaction with government increases by 0.028 points through the effect that income has on happiness. Yeah, so this is only about the indirect effect of income on satisfaction with government that runs through happiness. Now we know that this is represented by basically an indirect effect coefficient of 0.028, which we get by multiplying the A path with the B path. But then, well, how can we now say something about the statistical significance of this entire path? Because, well, that means we somehow have to combine these into a single hypothesis test. Well, the good news is there are a couple of different ways to actually do that, and one of the most popular ones is the so-called Zobel test, which is based on a Z distribution. So it's a version of a normal distribution test, where you say, well, take the coefficient for the A path, multiply it by the coefficient of the B path. So that's, in our example, that would be this 0.028 value, and then divide that by the square root of the A path squared times the standard error for the A path squared plus the B path squared plus the standard error for the B path squared plus the standard error for the A path squared multiplied by the standard error for the B path squared. And this is a way of statistically somehow combining both of these coefficients and their respective standard error in such a way that we know, okay, this will follow a Z distribution under the assumption that the null hypothesis is true. So that's a way of doing that. However, I would say, well, that's quite a complicated formula to really understand why that is and to remember. So I don't expect you to know this by heart or to do this manually. Instead, I posted an Excel sheet that I stole from some website where you can just fill in what you find in SPSS, and it will automatically calculate the result of this Zobel test for you. So if you want to go a bit further in testing your mediation hypothesis than just running through the 4 conditions, but also say something, well, is this indirect effect now also statistically significant? You can use this Zobel test, and for that you can use the Excel sheet that I'm posting on Brightspace. But the basic logic of the formula is that we are combining the coefficients by multiplying them, and then somehow we're combining the standard errors for those 2 coefficients in such a way that statistically that makes sense again. Yeah, there's a whole theory behind that, but you really don't need to worry about it. Yeah, so that's it for moderation and mediation analysis in practice. Of course, you will get to practice with them in the assignment. There's a couple of general remarks I want to make. If you go out into the real world and do moderation and mediation analysis, one thing is you should be aware that we are not talking about quite complicated models. which will tend to also try to estimate effects that tend to be quite small. So interaction effects tend to be a bit smaller than just normal regression effects that we normally are interested in. Mediation effects tend to be small because we have these indirect effects, which will be also only part of the original relationships. So basically, we have a situation where the models are relatively complicated and effects tend to be relatively small. So that means that basically we need a lot of observations to really reliably do moderation and mediation analysis, because we have not that much statistical power and there is a risk of overfitting that's quite large because you're introducing so much complexity to the models. So yes, of course, do it if you have a theoretical moderation or mediation hypothesis that you want to test, but be aware that you need a pretty good sample size to really reliably do that. How big, of course, it depends entirely exactly what variables and how much variation do you have and how large are the actual true effects. But yeah, remember that it's basically the more complicated you make your models, the more sample size you need to get reliable results. If you do moderation analysis, I would always recommend, only do that if you really have a clear theoretical reason to expect an interaction effect. Yeah, so if your theory says, well, there should be an interaction effect, yeah, of course, do it. Test an interaction hypothesis. So that's one situation where you can do that. The other situation you can consider it is if you maybe don't have a strong theoretical reasoning why you expect an interaction effect, but you see clear indications of there maybe being an interaction effect. And that would happen when you inspect residuals, like we discussed last week, and like I showed you in the example syntax that's posted on Brightspace. And sometimes you will see that in the pattern of these residuals, you will see this kind of strong pattern emerging, so that you see a kind of heteroscedasticity in the residuals emerging. Yeah, so this kind of non-standard variation of your residuals. And sometimes one of the reasons that happens can sometimes be because there is an interaction effect going on between the variables you have in your model, but you didn't include that interaction effect. So if you have that situation, you can sometimes consider including those interaction effects, but again, there I would be cautious. Yeah, do that if you have a large N, and you have very, very clear indications that there might be interaction effects, and if you can at least post hoc think about why it might be reasonable that there is this kind of interaction effect going on. Yeah, so sometimes that might be the case, but primarily really do that if you have a theoretical reason to expect an interaction effect. If you do it also, I would always recommend don't just immediately start with estimating interaction models. Just start with your normal regression models always. So just get a feeling of what the main effects are without taking into account any kind of interaction effects. And once you have estimated those, then add these interaction terms step by step. Yeah, so don't just start out with the first regression model that you're estimating for your research paper or report, with including 5 or 10 different interaction terms, because you want to do this step by step, so you also see when things go wrong or when you get weird estimates that don't make any sense anymore, because then you might be overfitting your data, so asking too much for the amount of data that you have. Yeah, so that's always a good idea. Mediation analysis, I showed you a very simple example where we didn't worry about any kind of control variables. Of course, often you will want to include control variables, and you can totally do that in those mediation models. But the added complexity is now we don't just have one model, we have multiple models that we're estimating, well, 3 for the mediation effect, which means that for each of those models you could think about, well, what control variables do I need for this model? And that can be a bit of a headache, because in theory you could say, well, maybe I'm going to use different control variables for different models. So maybe I'm using different control variables for the model for the mediator than I'm using for the model for the dependent variable in the simple relationship or the mediator relationship. And there are some situations where it can actually be relevant to do, but the problem is then how do you still compare across these different models if the control variables that you include, so the other variables that you include in your model, are different between them? And that's a real problem then, of course, because then you're not just changing the mediator variable, but you're also changing other things. So I would say if you're in doubt, always just include the same control variables in all models. That's always the best starting out point anyway. Yeah, so that if you want to say, well, I want to control for differences in age and income, or whatever, just include it in all the three models that you're estimating for your mediation effect. That's the least likely to go wrong. In general, there are more sophisticated ways of doing this mediation analysis than what I'm showing you here. This involves the estimation of so-called structural equation models. So this is sometimes referred to as SEM, so SEM just standing for structural equation modeling. So these are more sophisticated types of extensions of the regression analysis that we see in this course. So that goes way beyond the topics of this course. It might be something that you might encounter later. And those really allow you to, rather than having to separately estimate these three models for the mediation effect, to just do that all together jointly. So just have one overall model with all these pathways included in the model and estimated in one go. And so that gives you a lot of flexibility in what types of models you're estimating, and allows for a lot more sophisticated statistical analysis. But it's also quite complicated to do that. So this is something that maybe if you're super interested in mediation analysis, or later for your thesis, you might want to take a look at courses or books that are about that topic. Yeah, but for PSRM 2, thankfully for you, probably we are not going to go there just yet. Yeah, so that's it for me. I will be seeing you on Zoom. Hopefully, probably you will have questions about this stuff, so you know where to find me, and please do, because I love to help. I want to help, but you need to come to the Zoom sessions so I can actually help you. Yeah, okay, take care, bye-bye, and have fun with the assignment.